The unit circle is really important that we know it. What we're going to do on this digital copy, feel free before we write on it, make yourself like duplicate the page. If you go to the little circle with the 3 dots on the side, no, I'm sorry, pages, and then the 3 dots on the side, you can duplicate this page if you want it to practice. So if you want some practice before the quiz on Friday. I would just like to focus for a moment on some of the patterns that we find in the first quadrant. So this might help you, because remember, if you know the first quadrant, as we go around the circle, we just have to repeat things. All of the red ones match up, all of the green ones match up, and they don't have to be that color, but all of the blue ones, and so on. Okay. So what I would like to do is I would like to focus on our first quadrant. So remember, this is 0 degrees or 0 radians. This is 90 degrees or pi over 2 radians. So the easiest one right off the bat is 45, which is pi over 4, because you have to cut the 90 in half one more time. So 180 divided by 4 is 45. Now, this is 30 degrees, and this is 60 degrees. Now, remember, all around the circle, starting at 0, counting counterclockwise, this pattern, it always goes 30, 15, 15, 30, 30, 15, 15, 30, 30, 15, 15, 30, all the way around for a total of 360 degrees. So if you're ever if you're a little unclear as to about where you landed at, you can always do that trick. 30, 15, 15, 30, 30, 15, 15, as you go around. Another pattern that might be helpful to you is that if you want to find the radians and you're just unsure about how it relates, you can always put the degrees, tack on a pi, and put it over 180, and then reduce. So that is a formula that works for every single degree measure that we got. So technically, 90 pi over 180 reduces down to pi over 2. 45 relationship between how is this related to 180, which is pi. So if you know that 180 degrees is pi, you can take any of these. Now, it's going to take you longer because you're not going to be able to use a calculator on Friday. So it might take you longer to reduce it down. But that's why I like the trick. Once I know what 30 and 60 are, we're good to go. Now, 30 pi over 180, 30 goes into 180 6 times, because of the fact, just think about the fact that 3 goes into 18 6 times. So, 60 goes into 180 3 times. 60 pi over 180 would be pi over 3. Look at the numbers. These numbers keep getting, let me make my 6 look prettier. These numbers keep getting smaller. 6, 4, 3, 2. That isn't coincidence, because you're getting more closer to that full 180 mark, okay? All of the red ones should have a 6 denominator once reduced. All of the green ones, a 4. All of the blue ones, a 3 denominator once reduced. Everything is related to the first quadrant. Now let's talk about the points for just a moment. This point right here, the x is longer than the y. That's a good way to remember that the point that the square root of 3 over 2 comes first, then the 1/2. The x is longer than the y. That's a good way to remember that your square root of 3 over 2 comes first. Here, the x value and the y value are identical. It is an isosceles triangle. That's why you get square root of 2 over 2, square root of 2 over 2. Here, the same values we got for the 30 have just been turned on their head. This time, we're halfway for our x, and square root of 3 over 2 up. The x is the shorter one, so that's why it's 1/2 square root of 3 over 2. And then finally, our 0 and 90, let's put those on because I want to show you a pattern there. That's the point. Think about if I hit the circle with radius 1, that would be the point 1, 0, but this would be the point 0, 1. Okay. So again, I just want to focus on this first quadrant because there's so many patterns in it. And if you memorize the first quadrant, the rest just repeats itself. Now let's look at some other patterns that are really cool. Our longest x value occurs at 1. Our x values are always between -1 and +1. Nothing more, nothing less. Somewhere between -1 and +1. But look what's really cool. That's our longest one. And then the next x value is a little bit shorter. And the next x value is a little bit shorter. And the next x value is a little bit shorter until we have an x value of 0. Now, another pattern about the x values. Let's watch. This is really kind of interesting. This is square root of 4 over 2, right? Isn't that square root of 4 over 2? 1, the number 1 is square root of 4 over 2. Square root of 3 over 2, square root of 2 over 2, square root of 1 over 2, square root of 0 over 2. Kind of interesting pattern, right? Now, let's observe what we see about our y's. Our y's go the exact opposite direction. This time it starts at 0 and starts getting higher. Why? Because our y value starts at nothing. Now our y value is a little bit higher. Now our y value is a little bit higher until it reaches its highest value of 1. So our sine value is the largest it's ever going to be at 90 degrees. Look at these values. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. There is a pattern. So in everything you do in this circle, there is a pattern. Everything you see in the first quadrant will repeat itself into the other quadrants. But always start, when you want to repeat this pattern, always start from the x-axis and your pattern goes up. From the x-axis, your pattern goes up. From the x-axis, your pattern goes down. From the x-axis, the pattern goes down. All of this relates to where are you on the x-axis? How are the reference angles matching up in their relationship with the x-axis? That's why here, these ones match because those are the same distance from the x-axis. These ones match because those are the same distance from the x-axis, and so on. It's all about the patterns, and it is your responsibility to memorize this by Friday because we are going to be using this without a calculator for the rest of the school year. It's not going anywhere. You have to know this. If you take calculus someday in your future, you have to know these values. And again, even my calculus students, they'll remember the first quadrant and then they'll relate it to the other ones if it's something that falls in the other quadrants. Most of what you use in calculus, they kind of do tend to stick in that first quadrant, maybe first and second, but you got to know these patterns. Super important. Okay. So I've made a little chart for you where we can also look at the patterns, okay? Now remember, on the unit circle, the sine is our y, the cosine is our x, the tangent is y over x. The sine is our y, the cosine is our x, the tangent is y over x. Now let's do the radians. Remember, this is 0 radians. 30 pi over 180 reduces down to pi over 6. 45 pi over 180 reduces down to pi over 4. 60 pi over 180 is pi over 3. 90 pi over 180 is pi over 2. Let's write down the points over here on the side. At 0 degrees, the point that I hit on the unit circle is 1, 0. 30 is square root of 3 over 2, 1/2. 45, square root of 2 over 2, square root of 2 over 2. 60, 1/2 square root of 3 over 2. And then finally, 90 is 0, 1. No, yeah, yeah. Okay, I had to debate that in my brain there for a second. Okay. So I know that the sine of 0 degrees uses the y values at that location. So just go down the list. It's square root of 0 over 2. I'm going to actually write that. That's square root of 0 over 2. Square root of 1 over 2. Square root of 2 over 2. Square root of 3 over 2. Square root of 4 over 2. So it starts at its lowest value and then goes upward. The highest value the y ever reaches is 1. The lowest value the y ever reaches is at 270, negative 1. Okay, now let's pull out the x values. They go the opposite way. So we have them written already. So let's start down here. This is 0, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. Now, we've seen those enough. Hopefully those patterns are starting to get slightly attached to your brain, which is awesome. But now, for the first time, we need to do the tangent, which is also, we could say, sine over cosine. Since our y value on a unit circle is always the sine, and our which is y, and the x value is always our cosine, the tangent is y over x or sine over cosine. Okay, so if we do it in this order, and that's why I put it in this order, so we could do the y value over the x value. Okay, so this would be 0 over 1, which is 0. But I want to do the bottom one for a moment. So let's do 90 degrees. That would be 1 over 0, which is undefined. So if 0 is our numerator, that's perfectly great. It's 0. If you were to, at this moment, get out a calculator, put in the tangent of 0, you're going to get 0. But if you put in the tangent of 90, it's going to say either domain error, 0 division error, error of some sort, because it's undefined. You can't do 1 over 0. Great. So the ones I have on the back, I was told it says divide by 0 error. So that can kind of tell you that should be that 1 over 0 that you get. But I just want either the word undefined or the null set. The word undefined or the null set, whatever you want to write. Okay. Either is acceptable to me. Okay. So those two, 0, 90, 180, 270, they're always going to be either 0 or undefined. Okay. For the tangent. Let's do 30, 45, and 60 because they get a little funky on how to reduce them. I'm going to give you a trick. If we have a fraction divided by a fraction and it looks like that, what I call a complex fraction, what you can do is a trick called big C over little c. The multiplication of the outer 2, connected by a big C, will go on the top. The multiplication of the inner 2, little c, will go on the bottom. And then you can reduce it how you want to. So I always do when I have a complex fraction like that, big C over little c. It's a great trick. I use it and I remind my calculus students. Because what's happening is to divide by a fraction, we multiply by the reciprocal. So then the D would go on top and the C would go on the bottom. So it just is a nice little trick. So you'll see that I will do that. Okay, so let's start with 30. 30, it's going to be the y value over the x value. So it's 1/2 over square root of 3 over 2. Now, let's do big C over little c. Now, I don't actually physically do the multiplication. What I like to do is I like to just put, what am I trying to multiply on top? What am I trying to multiply on the bottom? Can I reduce it, make it pretty, blah, blah, blah. Okay, so on the top, I have the big C, the outers, 1 times 2. The little c is the multiplication of the inner stuff. That's 2 and radical 3. Now, the reason I don't like to multiply it right off the bat is because many times things will reduce. The 2's are going to reduce, leaving me 1 over radical 3, which once rationalized is radical 3 over 3. So if I said to you, what is the tangent of 30 degrees? What is the tangent of pi over 6. It is always exactly radical 3 over 3. If you put radical 3 over 3 into a calculator and got the decimal value, and if you hit the tangent of 30 on a calculator, it would be that exact same decimal value. Remember how one of the things I focused on when we were learning right triangle trig was the exact values, how I wanted exact values that you sometimes needed to leave square roots, fractions. This is the exact value. If you put the decimal value in, it is incorrect. You got to give me an exact value. Okay, let's do now 45 degrees. Now 45 degrees is nice because if we take the y value square root of 2 over 2 divided by the x value square root of 2 over 2, if we do the big C over little c trick, or if you just contemplate, if I divide by something that's exact match, you always get 1. But watch, we get 2 radical 2 over 2 radical 2, which is indeed 1. So the tangent of 45 is the ratio of the legs. The legs form an isosceles triangle in a 45-45 right triangle. So the fact is that's why we get a 1. And then finally, let's do the tangent of 60 degrees. If we put the y value square root of 3 over 2 over 1/2, please let's do our big C over little c trick. This time on the top, we have a square root of 3 and a 2. This time on the bottom, we have a 2 and a 1. The 2's cancel, leaving me with radical 3 over 1, which is radical 3. Some interesting facts. The tangent of 30 and the tangent of 60 will be reciprocals. Now, why is that? Well, if one, the opposite and adjacent are one thing, the other, it flips it around because of where you're looking from that particular 60 instead of 30 angle. So they are reciprocals. So anytime they're complements, they're going to be reciprocals. So that is just another tool that can help you to have those patterns memorized, okay? And we're going to practice more tangents. We're going to eventually practice our secants, our cosecants, and our cotangents. I think we maybe get to that tomorrow is my guess. Okay. Do we have any questions about the chart that we see here that helps us to memorize them even further? Good? Okay. So let's actually practice using our unit circle. So if you want to have your paper copy in front of you, this is a good time to have that out. 4 pi over 3, if you think about the fact that pi over 3 is 60, 4 of those is 240. I am a person that thinks better in degree measures. So if that tells you anything. Once I know that 4 pi over 3 is the 60 down here, its reference angle is pi over 3, it's 60 degrees. So that is just the point related to 60 down in the third quadrant. The point related to 60 is that 1/2 square root of 3 over 2, but they're both negative down there. So that's negative 1/2, negative square root of 3 over 2. So I have that memorized. So I can tell you the sign of 240 very, very quickly. I know it is the y value at 240. So the answer is negative square root of 3 over 2. So by knowing my unit circle and having that value of pi over 3 memorized, 1/2 square root of 3 over 2, I can put it into the correct quadrant, and then I can find the y value is my sign. That's it. That's as simple as it is. So that's how useful our unit circle can be. Let's talk about 150. 150, if you were to draw it, 150 has a reference of 30. So it's related to our 30 value, but it's in the second quadrant. So instead of square root of 3 over 2 1/2, let's make it negative square root of 3 over 2 positive 1/2. So the tangent of 150 is the y value, 1/2, over the x value, negative square root of 3 over 2. Now the tangent is always negative. in the second and the fourth quadrant because it'll be a positive over a negative in those quadrants. The tangent is positive here and here. So I should expect a negative value, which you can tell I'm going to get a negative. Let's do big C over little c because that's a really great trick for these. The outer two, big C connects, and that's 1 times 2. The inner two connect, and that goes on the bottom. That's negative 2 times radical 3. The 2's cancel. Let's put the negative in the top. So we get negative 1 over radical 3. You got to rationalize. Our final answer is negative radical 3 over 3. So that is how we find the exact value of the tangent of 150. Just like before when we were doing right triangle trig, if it said exact value, how I didn't want you to give me the decimal value from a calculator, the unit circle allows us to find an exact value without a calculator. So that's why we memorize it, because we can have those exact values, which is more accurate when it comes to some applications and stuff. Okay, let's talk about the secant of 15 pi over 4. Now, 15 divided by 4 is 3.75. It's more than 2 pi, right? 8 pi over 4 is 2 pi. So 15 pi over 4 is more than a cycle around the circle. So the first thing I would do when I see this problem is let's take off 2 pi's, which is 8 pi over 4. If it's 4 denominator, just double the top. 4 goes into 8 2 times. And that's 7 pi over 4. So I'm really going to be finding the secant of 7 pi over 4 because I have to find the location on the unit circle. Okay. Now pi over 4s are 45s. So I'm going to break this into 45-degree wedges. Remember that perfect X, the green one that you did? Okay. So let's loop around our circle for a moment. Okay. We need 7 45s. So 1, 2, 3, 4, 5, 6, 7. We're right here. Okay. So we're the 45. Pi over 4 should already tell you square root of 2 over 2, square root of 2 over 2 is going to be useful. But in this location, the X is positive, the Y is negative. Okay. Okay. So now we found the point. Once we find the point at that location, we got what we need to answer the question. So what is the secant? Well, the secant is the reciprocal of a cosine. So the cosine of 7 pi over 4, which is the same as 15 pi over 4, is square root of 2 over 2. It's that X value. Okay, the cosine is your X value. So all we got to do is flip that over and just get it prettier. Okay, so if we flip it over, we get 2 over radical 2. Is that in the form you want radicals to be, radical fractions? Do we want to keep it like that? No. Are we allowed to have that radical in our denominator? No. So I'm going to show you a trick. Well, something interesting happens. If I multiply by radical 2 on top and bottom, I get 2 radical 2 over 4. No, I don't. I get 2 radical 2 over 2, which is radical 2. So the reciprocal of radical 2 over 2 is radical 2. The reciprocal of radical 5 over 5 is radical 5. The reciprocal of radical 7 over 7 is radical 7. So the reciprocal of radical A over A is always just a plain old radical A. So radical 2 over 2, when you flip it over, is radical 2. And if you memorize that, fine. If not, just do what I just did, rationalize it, and we should get an answer. Since the cosine is radical 2 over 2, the secant at that location is just a square root of 2. Okay? So that is one of the ways that we have to use the unit circle. That's why we memorize the unit circle, so that we can answer questions like that. Do we have any questions about example 4? Okay, let's do some more. So 7 pi over 6, we know is related to pi over 6. It's related to 30. It's technically 210, Again, I like to think in degrees. It helps my brain a little bit. 210 is down here. The point at 30, hopefully you're starting to see those. That is square root of 3 over 2, 1/2. But in that quadrant, they're both negative. So just stick a negative. That's a 30 reference in the third quadrant. So the sign, what value do we use from that point? Do we use the negative square root of 3 over 2, or do we use the negative 1/2 when finding the sign? Exactly, we use that y value. So the answer is negative 1/2. So the sine of 7 pi over 6 is the same as the sine of 210. Reference angle 30. What's 30 in that quadrant? Negative square root of 3 over 2, negative 1/2. Let's look at cosine of pi over 3. Pi over 3 is 60. 60 is in the first quadrant. We always love the first quadrant ones. So that is the point 1/2 square root of 3 over 2. The cosine is my x value. So the cosine of 60 or pi over 3 is 1/2. 4 pi over 3 for number 7C is related to a pi over 3. That denominator, that's one thing I do like about radians. It kind of tells me what to look for. It's related to 60 somehow. 4 60s is 240. 240 down here is the point on negative 1/2 negative square root of 3 over 2. Now the tangent, remember, is the y value over the x value. So the tangent of 4 pi over 3, just take my y value, negative square root of 3 over 2, over my x value, negative 1/2. Now the two negatives are going to make a positive. The tangent is positive down in the third quadrant. If we do big C over little c, on top we get 2 radical 3. On the bottom we get 2 times 1. The 2's cancel. It's radical 3 over 1 or radical 3. So the tangent at our 4 pi over 3 location is related to 60 degrees, and in that quadrant it will give us a positive tangent value of radical 3. Does that make sense how we're using this? Everybody okay with that example? So find the location and then do with the point what you're supposed to do with the point. If it's a cosine, use the x. If it's a sine, use the y. If it's a tangent, use y over x. If it's one of the reciprocals, you got to flip the appropriate one. Okay, let's take a look at D. The secant of 270. 270 is down here. The point at 270 is 0, negative 1. The cosine of 270 is 0. And you can put that over 1 if you have the urge, because we need to take the reciprocal. The secant of 270 is 1 over 0. Now, anytime you get a 0 denominator, a 0 numerator, 0, but a 0 denominator is always undefined. So you can write undefined like they've given us in the instructions, or you can write the null set. That's okay by me as well. So if you get a 0 denominator, if you're trying to flip over something that is 0, just say undefined or give me the little null set symbol. Okay. Does everybody got D? Any questions about that one? Let's keep going. Now, what they're trying to get at with example 8 is the fact that those values are not on the unit circle, but they can be. In lesson 7-2, I think, we talked about coterminal. How do we land in the same location? So if I can find where it lands, that's all I need. If it's more than 2 pi, so 4 goes, 2 is 8/4. So 9 pi over 4, if I take away 8 pi over 4, just double that bottom, is 1 pi over 4. This is coterminal with pi over 4. So as long as I know where it lands, I'm golden. If I know where it lands, I know what to do. 45 degrees is pi over 4. I love the first quadrant values. It's square root of 2 over 2, square root of 2 over 2. So 9 pi over 4 gets us there. Now, if you didn't notice that, count how many 45s. 1, 2, 3, 4, 5, 6, 7, 8, 9 lands us there. So if you actually count it out, or if you do a coterminal trick, take off 2 pi's, or in this case, 8 pi's over 4, however you slice it, we land at 45 degrees. The cosine there is square root of 2 over 2. Now, if you have a negative degrees, add 360 until it's not negative anymore. If you have a negative radians, add 2 pi's until it's not negative anymore. Or you can always convert. You can always convert to degrees and then work from there. Yes. Exactly. So, and the question was, how did I recognize that 9 pi over 4 was more than what I needed? If the top is more than double the bottom, so 8 pi over 4 gets us a loop around, so 9 pi over 4 is an extra one. So however you want to do it, you can actually count it out. Count pi over 4s if you want to. That's 45. And remove an extra 2 pi. Okay. However you do it, there's lots of ways to do it. You can make it degrees. That's one thing you can do. You can make it all degrees and then take off 360s until it's what you want. It'll also go back to 45, however you want to do it. So in B, negative 300 isn't something that I see right on the unit circle. But if I add 360, negative 300 is the same as 60 degrees. So I can just take the sign of 60 will answer the question. It lands me in the same spot. It is coterminal at that spot. So adding 360 or subtracting 360 or adding 2 pi and subtracting 2 pi will get you what you want. And so 60 is the point 1/2 square root of 3 over 2. Sine is our y value at that location. The answer to this is square root of 3 over 2. So where did I land, even if I got there in a non-traditional way? Where do you land? And that's the point you get to use. Here's another one. 29 pi over 6, double 20, or double 6, you get 12, right? So take off 12 pi over 6. I get 17 pi over 6. I'm still a loop extra around. Take off another 12. Oh, now I can find where I land. Because the first loop, the first 12 pi over 6 gets me perfectly around. Another one gets me perfectly around. And then I would go an extra 5 pi over 6. So now I get to use the pi over 6 in our second quadrant. Pi over 6 is 30. 5 pi over 6 is 150. We actually land in the 150 spot, which is the point negative square root of 3 over 2, 1/2. So the tangent, excuse me, of 29 pi over 6 is the same as the tangent of 5 pi over 6. We just do the y over the x. Y over x at that location. Now, here's a perfect candidate for big C over little c. So let's do that so we can get that into reduced radical form. On top, I would get 2 times 1. On the bottom, I would get 2 times negative radical 3. Always just pop that negative out in front or in the top. The 2's cancel perfectly, leaving me negative 1 over radical 3, which needs rationalized. But that just pops that radical to the top and leaves a 3 behind when I do that. Okay, so the tangent of any pi over 6 will always be radical 3 over 3, sometimes positive, sometimes negative. The tangent of any pi over 3 is always going to be pi over, or square root of 3. So there is a pattern that happens, yes. Okay, does everybody see how we find ones that land in a somewhat non-traditional way? Find where it lands, use that point. Yeah. Oh, you can't, but it does. So you can count out the number of like if it's a pi over 4 or pi over 6, you know that pi over 4 is 45s. You can count out the 45s and land in that spot. If it's pi over 6s, you can count the 30s until you land in that spot. You're welcome to do that. So there's so many ways to do the same thing. Yes, you can do that. Definitely. Okay. So you can use multiples of that, double. There's lots of ways to do it. Yeah, because you're really just thinking about if I've looped around and started where I came from, just take that off if you can. Yep. Nope, that does work. Okay. So now here is your homework. Okay. See where it says to find the exact value. Yes, you're going to be using the unit circle the whole time. Okay. For these ones, you're sketching the angle and nothing more. These ones are unit circle values. The top ones are unit circle values. The bottom ones are unit circle values. But here's what I want to see on your paper. Okay. I don't just want to see the answer, because you can look at your neighbor's paper who might have done it the night before and just write all those down. I at least want you to write the following. For pi over 2, number 9, please first give me the point at that location. So I want to see 0, 1, and I want to see that that's equal to the 1. So I want the point and the value. Okay. Negative 180 is the same as positive 180. It's just looping backwards. So the point there we can write down at negative 180 is negative 1, 0. So write down the point and then do the value. Tangent is y over x. So cotangent is the x over the y. It's negative 1 over 0, which is undefined. Okay, so that's what I want to see. What point did you land at? Then do the value. What point did you land at for all of these? And then do the value. Except for 17, 19, 21, and 23, please put the, just sketch the angle and find the reference over on the side. So that's it. This is due at the beginning of class tomorrow, so if you have any questions, you can ask at the beginning of class. You can probably get a ton of it done right now. Please recall, you're going to have your unit circle memorized by Friday. On the back table, there are some extra of the big papers, so if any of you are a person that writing it one more time is going to help you, feel free to grab the papers. There's also little copies if you want a little copy to try to repeat the process. In mathematics, repeating the process is a really good way to study. So there you go. You have the remainder of class, please, to work on this 7.3b homework, which is due at the beginning of class tomorrow. Okay, so there you go.